2023 AP Chemistry Free Response Question 1. Part A, we're told that manganese has several common oxidation states, and we're asked to write its complete electron configuration. A quick glance at the periodic table tells us that manganese's atomic number is 25, so its nucleus contains 25 protons. Because it's in its ground state, this also means that manganese has a neutral charge and so has 25 electrons. So to write the electron configuration, we just have to follow the electron orbital pairing rules until we get to the number 25. 4s2, 3d, and now we check to see 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. So in order to get to 25, we just have to add 5. Manganese forms cations. Electrons are lost from which subshell first? Although you might be tempted to write 3d here, 3d is actually not the right answer because the force between protons in the nucleus and electrons in the 4th energy level is weaker than that of those in the 3rd energy level. Therefore, electrons will first leave the 4s subshell. Now, a student performs an experiment to produce a manganese salt and determine its empirical formula. They do this by placing a sample of solid manganese in a beaker containing excess aqueous hydrochloric acid, as represented by this equation. We're given the following data about the mass of the beaker and manganese solid and the beaker and the manganese salt, and we're asked to calculate the mass of chloride in a sample of the manganese salt remaining in the beaker. So in order to get the mass of chloride, we simply have to subtract equation 2 from equation 3, and that's going to leave us with the amount of chloride. In order to calculate the number of moles of chloride in the sample, we just have to divide the number of grams of chloride by its molar mass. For part D, the student determines that 0.0199 moles of manganese were used, and we want to use this to calculate the empirical formula, basically to find x and y, or the ratio between moles of manganese and moles of chloride. So just dividing gives us the ratio of these two, and we can confirm that for every mole of manganese used in this experiment, 2 moles of chloride are used. So x must be 1 and y must be 2. For part E, the student repeats the experiment, but notices that some of the manganese salt splatters out of the beaker, and we're asked about the number of moles of chloride calculated. Will it be greater than, less than, or equal to what we calculated in part C? So the way to think about this is just to think about how we calculated the number of moles of chloride originally. It was just taking the mass of the beaker and the manganese salt and subtracting the mass of the beaker and manganese, and then we can just use this value to get our moles of chloride. And so what's changing here is the mass of the beaker and the manganese salt. It's simply decreasing now because some of it is splattering out of the beaker. This value will just decrease, and so our calculated gram value of chloride will decrease, thus decreasing the calculated moles of chloride. For part F, we're told that another compound of manganese, manganese dioxide, is used in batteries, and we're given some half reactions in this table right here. Part 1 is asking us to write the balanced net ionic equation for the reaction that has the greatest thermodynamic favorability. What we need to know for this question is that thermodynamic favorability is basically spontaneity is based on delta G. So we want to make sure our delta G, which is equal to negative NFE, stays negative, which means that our value for E, as shown here, must be positive. And so we're looking for a combination of 2 of these half reactions to get us the full reaction, where our value of E is the most positive. And so the combination that could produce that would be if we negate the second one and add it to the third one. And this would work because if we negate this second equation, we'll have 2 electrons on the right side, and that will cancel out with these 2 electrons on the left side. So now we can see that the hydroxides will cancel along with the electrons and the waters. And we're left with, in order to calculate the value of the electric potential for this overall reaction, we just have to negate the second one and add it to the third one, positive 1.43. In order to calculate the Gibbs free energy in kilojoules per moles, we're going to have to use a bit of dimensional analysis. N is simply the number of moles of electrons per 1 mole of the reaction, which basically just means that the reaction has all coefficients in simplified terms. F is just Faraday's constant, where the units of this is coulombs divided by moles of electrons, and our electric potential is in volts, which is the units of joules per coulomb. We also have to make sure to convert the value of joules to kilojoules. And of course, it's good to confirm that our value of delta G is negative, which means that our reaction is indeed spontaneous. For part 4, we're told that a student claims the total mass of the alkaline battery decreases because the anode, the negative side, is losing mass. We're asked if we agree with the student's claim. So this just requires a bit of logical thinking, and we must realize that the battery is in a sealed compartment, which means that it's a closed system, so unaffected by the outside world. We know that mass is always conserved in a closed system. Specifically, the total mass of the battery will not change. Like and follow for more.